This video is going to cover Section 3.5, Applications of Exponential and Logarithmic Functions. There are five common mathematical models that are both exponential or logarithmic: exponential growth, exponential decay, the Gaussian model, logistic growth, and logarithmic model. We are only going to be dealing with exponential growth and decay and then the logistic growth model. The Gaussian model is used for determining SAT and ACT scores, and then the logarithmic model is used in calculating magnitude of earthquakes, but we're only going to be focusing on the first two and the fourth one. The first one is exponential growth and decay, and I'm going to kind of combine these because the equation is very similar except for one little difference. A couple examples of where you would see exponential growth or decay would be with populations, half-life, pyramid or Ponzi schemes, and then also investments, and these are just to name a few. The model is y equals ae to the rx or y equals ae to the negative rx. The one on the left is exponential growth and the one on the right is exponential decay. Now you'll notice that we have base e in these. We're no longer going to have like a base of 2 or a base of 3 if something doubles or triples. We're always going to use a base of e. A represents the initial amount or population, x is time, r is a constant, you might also see k, and then also for time you might also see the letter t. And then y is the amount or population after a certain amount of time has passed. The graphs look like this. Exponential growth is on the left and exponential decay is on the right. You'll notice that they both have horizontal asymptotes at y equals 0, and that's because just for a basic exponential equation, there is no exponent that you can raise a number to get a negative number. You're always going to get close to 0, but you're never going to pass that line. So the first example I have is regarding bacteria growth, and it says inspectors for the Fulton County Health Department routinely check food samples for the presence of the E. coli bacteria. When E. coli are placed in a medium that provides nutrients needed for growth, the bacteria population can increase exponentially, reproducing itself every 15 minutes. If an inspector has a sample containing 1,000 bacteria cells, how long will it take the population to reach 64,000 cells? So since we said it was going to increase exponentially, we're going to use the equation y equals ae to the rx. A couple things that you need to do before you can answer the question is that you have to solve for any constants that are in the equation. And so for this one, since r is the constant, we're going to solve for that by plugging in the information that we're given. And then once we have that equation, we'll use it to answer any other questions. So we are given three important bits of information. The fact that the cells reproduces itself in 15 minutes, and it started with 1,000 cells. So what that's going to look like when we plug in is the 1,000 cells, that's our A, e to the r times 15. So the 15 was the time that passed, and that's the time that it takes it to reproduce itself, and reproducing itself is the same thing as doubling. So I had 1,000 cells, in 15 minutes it reproduced itself, so that makes 2,000 cells. So then we want to solve for r, that constant. So the first thing is to divide both sides by 1,000, and then we learned this in Section 3.4. How do I solve for an exponent when I have a base of e? Well, we need to apply the inverse of e, which is ln, but do that to both sides. So we get ln of 2 equals ln of e to the r times 15. That right side is going to simplify to just r times 15. So to get r by itself, we need to divide both sides by 15, and we get an r value of 0.0462. Next, I'm going to plug that into the equation, and then here is my exponential growth model that I can use to answer any questions. So if I were to ask how many cells are there after 10 minutes, you would plug 10 in for x. If I asked you how many after 30 minutes, you'd plug 30 in for x. But since the question was asking how long will it take to reach 64,000 cells, I'm asking for how long, so I'm asking to solve for time. That means we're going to plug 64,000 in for y and solve for x. So then we're going to divide both sides by 1,000 and then apply the same things that we did when we solved for r. So in order to bring the exponent down, you have to apply the ln to both sides. So the natural log of 64 equals the natural log of e to the 0.0462x. That ln and e cancel out on the right side, and so then my last step would be to divide by the 0.0462. So we get about 90 minutes or an hour and a half for the 1,000 cells to become 64,000 cells. Another example that we have of exponential decay is called Newton's law of cooling. Now the formula is a little bit different. It's y equals ae to the negative kt. You could still use negative rx, but then you'll notice that this has this plus c. And this C out here is actually the new horizontal asymptote because we've shifted the graph up, and so then the graph won't ever go below that C value. So what each part represents, the first part is that C, or our horizontal asymptote, is the temperature of the medium surrounding the object. And that just means it could be the room temperature, it could be the temperature of the cooler, the refrigerator, the freezer, or an oven, depending on what the object is in. A is the difference between what the object has been heated to and room temperature. So you don't want to say that it's initial temperature anymore. It's the difference between what the object has been heated to and room temperature. T is time, and that's always in minutes. So if I give you a time in hours, you always need to convert it to minutes. And then K is the constant that we need to solve for. So I have an example here that's different from the one on your page. I simplified it. The one on your page, it takes a little bit more time. So just change it to a beaker of water has been heated to 200 degrees in a room that is 72 degrees Fahrenheit. After an hour and a half, the water is 124 degrees. Now we're going to use this. We need to come up with a model. I don't have any questions to answer yet, but we need to come up with the equation to use. So the very first thing that you want to do is solve for A. And so remember, that's the difference between what the object has been heated to and room temp. Well, it says the water has been heated to 200 degrees and the room temperature is 72. So my A value is going to be 200 minus 72, or 128. The second step with a Newton's law of cooling problem is to solve for the K value, the constant. So we have A is 128. We want to solve for the K constant by plugging in the other given point. And it says after an hour and a half, the water is 124 degrees. Well, I need to convert that hour and a half to minutes because Newton's law of cooling is always in minutes. And then the 124 is the Y value. So an hour and a half in minutes is 90 minutes. And then the 124 is what I'm going to plug in for Y. So now I'm going to solve for the exponent here, the K that's in the exponent. So here's my equation. The first thing I'm going to do is subtract 72 from both sides and then divide by 128. That's how I get the 0.40625. Then I need to apply the natural log to both sides. So I get natural log of 0.40625 equals negative 90K. Last thing to do is to divide by negative 90, and you get a K value of 0.01. So I'm going to plug everything I know into the equation, and here is my model. So Y equals 128 is A, e to the, now you'll notice I made my K value negative. It becomes negative when you put it into the equation. So negative 0.01T and then plus 72 the room temp. So it says, what will the temperature be after 30 minutes? Well, that 30 is time, so I'm going to plug that in for T, and I get about 166.8 degrees. Nothing to solve for, you can just plug this into your calculator and get the answer. Nothing to move over to the other side. Another question I might ask is, when will the water reach 80 degrees? So this time we're going to plug 80 in for Y and then solve for time. So I'm going to subtract 72 from both sides, divide by 128, and then maybe that's on the next page. Nope. Sorry about that. So divide, first subtract 72 from both sides, then divide by 128, then apply the natural log to both sides, and then divide by negative 0.01T. We can go over this in class on Monday. Another exponential growth or decay is called compound interest. Now in Algebra 2, you should have learned the formula on the left, 1 plus r over n to the nt, and that's multiplied by the p. On the right now is a new one called A equals PE to the RT, and that's called PERT, and this is used for continuous compounding. So what those different variables represent, A is the balance in the account, so this is talking about investing money. P is the principal or the initial amount. T is time, and that's always in years. N is the number of compoundings per year, and R is the annual interest rate, and you always want to convert this to a decimal. So the example I have here is that you decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first pays 7% per year compounded monthly. The second pays 6.85% per year compounded continuously. Which is the better investment? So we need to plug what we know into the two equations. So here are our two models. Our $8,000 is our initial investment. The interest rate for continuous compounding is 0.0685. That's what my R has been changed to. And then it's for 6 years that I want to invest it. And when you plug that into your calculator, you get $12,066.60. On the left, I have the model that is used for compounding monthly. And so I have 8,000 times 1 plus 0.07, that's my 7%. I have to divide that by 12 months. Add that to 1, because anytime you are increasing in a percentage, you always add that decimal to 1. And then I'm going to raise that to the 12 times 6 power, because there's 12 months in a year for 6 years. That would be 72 months. And I get $12,160.84. So in comparison here, the better investment would be the compounding monthly for 7%. Now, I will tell you this, I don't have this example on here, but continuous compounding is always better if you have the exact same rate. So if this had been a 7% for 6 years, this amount here would have been more than the $12,160. The more times you compound in a year, the better off your investment is. But if the two percentages are different, you have to do the work, show the work to prove which one is better. And so in this case, the compounding monthly. But if they were the same interest rate, compounding continuously is always the better investment. And then the last model that we are going to walk through is called the logistic growth model. This is where you can see population growth, where there is limited resources and a carrying capacity. So for example, if you are studying a population of lions in the African desert, the population growth is not going to always increase. It's not going to be exponential because there's only so many resources for them to eat, and so there isn't going to be enough resources to hold an unlimited amount of lions. So logistic growth is going to have a horizontal asymptote that has a carrying capacity. Another example would be human growth. Growth of tumors or spread of disease is another one, and then chemical reactions. The model for logistic growth looks like this. Y equals A divided by 1 plus BE to the negative RX. And A represents the capacity or the max population. X represents time, that might be in T. Both B and R are constants. And then Y is the population after time X or T, whichever variable you have in there. So the example of the graph that I have is, it kind of looks like exponential at the beginning, and then it slowly fades off and it reaches this horizontal asymptote, and that's what our A value is. That's the max capacity. So the example I have is an example of a spreading of a rumor at a high school. It says at Bayside High School, the spread of a rumor can be modeled by a logistic function. Suppose a school has 1,000 students. At 8 a.m., 80 people have heard a rumor, and by noon, half the school has heard it. So I'm going to walk you through the steps in coming up with the model. The first thing that we need to do is solve for B. That's always going to be the first one we solve for in a logistic growth model. So we're going to plug in the initial value and the carrying capacity. So it said at 8 a.m., 80 people have heard the rumor. We can't plug in 8 for our X. We're going to say that 8 a.m. is represented by time T equals 0. So I plugged in 0 for the time, 80 for Y, and 1,000 in for the carrying capacity, because this high school only has 1,000 students. So forgetting about all social media, if you had a rumor just in a high school, it can only reach the 1,000 students that the high school has. So what you can do anytime you have a fraction and you have the variable on the bottom is you can swap the two parts. So 80 is going to be swapped with the 1 plus BE to the negative R times 0. And so then 1,000 divided by 80 is 12.5. E to the 0 power is what? Anything to the 0 power is 1. So then we're just left with 1 plus B, and then minus 1 from both sides. And we get a B, our constant, to be 11.5. The other constant we have to solve for is R, and then this is where we plug in the other point that we're given. So we're going to plug in 1,000, plug in the B that we just solved for, and then it said at noon 500 or half the school had heard the rumor. And noon is 4 hours after 8 a.m., so that's why I have 4 plugged in for the time, and then 500 since that's half the student population. Then once again, since the variable is on the bottom, I can swap the left side with the bottom. So then I get 1 plus 11.5 e to the negative R times 4 equals 1,000 over 500, which is going to turn to 2. And then just get your base and the exponent by itself so that we can bring that exponent down. So minus 1 and then divide by 11.5, and then take the natural log to both sides and then divide by a negative 4, and you get an R value of 0.61. So then it says write an equation that models the spread of the rumor. So here it is with the B and the R plugged in. The R does become negative when you plug it into the equation. And now we're going to use this to answer a couple of questions. It says about how many students have heard the rumor by 4:30 p.m. Since I'm asking for how many students, that means I'm going to solve for y, and we need to plug in a value for x. Now I'm not going to plug in 4.3. Time is represented by the hours passed since 8 a.m. And 4:30 is 8.5 hours after 8 a.m., so I plug that in for x. And then you can just plug this into your calculator to get the answer. You don't have to get anything over to the other side, and you get about 940 students. Make sure your answer makes sense. You don't want to have decimals here because you can't have a fraction of a student. And then the last question is, it says, when will 99% of the students have heard the rumor? Well, the population is 1,000. 99% of 1,000 is 990 students. So I'm going to plug that in for y and solve for x. Since I'm asking a when question, that means I'm solving for time. Then I have 1 plus, remember you can swap the left side with the bottom anytime you have a variable on the bottom. So 1 plus 11.5 e to the negative 0.61x equals 1.01 minus 1 from both sides and then divide by 11.5. And then the last step would be to take natural log to both sides to bring that exponent down. And then you need to divide by negative 0.61 to get x by itself, and I get 11.55 hours. Now remember, x is represented by hours after 8 a.m., so 11.55 hours is going to be 7:33 p.m. is when 99% of the students have heard the rumor. And this video covered the exponential models and logarithmic models that we're going to be using to hit targets 3.4 and 3.5.